mean, there's a direct URL for this, but it's easier.
All right, it's 9:30, so we're going to go ahead and get started, although there's still a little administrative stuff going on here to my right. So welcome to IETF 124 and welcome to Quantum Internet Research Group with the first meeting of Monday morning. Let me run through the chair's slides here briefly before we get started. As a reminder, you should all have signed in via the QR code, which I just eliminated from the screen here, but there are copies of it floating around. Let's see if I can do this properly. All right, so this is IETF 124, Quantum Internet Research Group, and as a reminder, this session is being recorded. Excuse me. This slide and the next couple are the note well for IRTF, and my co-chair Wojtek Kozlowski, who is online, pointed out that I actually have the old version of this note well here in the slides, and I saw the message from Wojtek too late to get this updated. But the standard note well follows intellectual property, the usual rights, as you can see on the screen there, and also audio and video recordings. Everything in the room here is being recorded, so if you come to the mic line or anything like that, you're consenting to have that recorded and included in any recordings or transcripts. And as always, privacy and the code of conduct. Everybody, the golden rule applies here. Treat everybody the way you would like to be treated. If you need a little more detail than that, there are multiple versions of IETF and IRTF codes of conduct floating out here. The very last line of this slide is the link to the new RFC 9775, which is in fact the IRTF code of conduct. And as a reminder, the goal of the IRTF is to focus on longer term research issues. We do not do standards here within IRTF, and IRTF publishes informational or experimental documents like RFCs, although not exclusively RFCs. And if you need any additional information, see RFC 7418. Usual tips, since this is Monday morning, it's actually worth reminding people, especially if there are any new participants in the room. Please make sure you have signed in using the QR code or directly through the data tracker website. And use Meet Echo to join the mic queue. We will be running the mic queue through the online system. So if you come up and stand up at the mic, you are invisible unless you have clicked on joining the queue. Remote participants, please make sure your audio and video is off unless you're actually presenting. And actually, this is a little bit out of date. I'm afraid I should have updated this slide as well. But you'll find the online tools through the agenda in the data tracker. All right, and so a couple of things real quick. We have a very full agenda this morning. We have about 8 or 9 things on the agenda, so most of this is going to be pretty short. Or most of the individual presentations are going to be pretty short, and we will keep the things to the appropriate time as we go. Document status, we have a couple of documents that are actually in process, as well as the 2 RFCs that were published earlier, which I didn't list here. Diego Lopez and company have produced an updated version of their quantum internet multiplane proposal, and so this is it's worth noting that this is still an individual contribution. It hasn't actually been adopted by the RG. And then we have a brand new one from Alan Zhu and Robert Proberger and their collaborators. Was submitted on the 1st of October, and we have not yet had any discussion, so today will be the first time to cover that, and that'll be the last thing on the agenda today. And with that, let's see, just as a reminder, I'm Rod Van Meter, the co-chair of QIRG. My co-chair is Wojtek Kozlowski, who's online and not able to speak very well. And we've drafted one additional person up here. Want to say hi?
Hi, I'm Brian Trammell, and I'm actually looking forward to learning about what the quantum internet is. So, I mean, I'm in the wrong seat for that, but we'll see.
Brian's going to help me run the queue in the meeting and everything else. All right, Inder, you are up. First presentation is
Yes,
Inder
it's
Monga.
Different.
Whoops.
It's a different presentation.
Whoops.
Yeah.
I grabbed the first thing. Apparently, I don't have them in order. I thought I did have them in order.
Yeah. Yep.
InterQNet. Let's see. Is this the right one? That's so which one? Oh, there we go.
Extensible software.
Sorry.
Yeah.
There we go.
You
They
grab-
are in the
you
right
can-
order.
You can grab the thing and then
I have to give you
Wait, over
control here. Where do I give him control?
here, I'll show you. You can click on the slides clicker and then you pass slides control.
Okay, I'm going
All
to
right.
flaunt my new participant thing, which I put on because I have forgotten. Okay, thank you guys. Time is quick, so I'll go quickly. So I'm going to talk
Stand a
about,
little closer to the mic.
I'm going to talk more about the software stack that we have developed today, not talk about the project or the results that we have accomplished. So, clicker.
Should be working. Slides clicker.
I am showing that you have control, but you know what? Just say next slide.
Next slide.
I will take back control from the slides clicker. So, there we go.
Okay. So the main thing I want to talk about software stack is, that we need quantum hardware, but you also need a software stack to make the quantum network work. So what we're talking about is a control plane that we have developed. On the left-hand side, you see the diagram, kind of a notional diagram of a quantum network. And on the right-hand side, you see how these different kind of interact with the quantum network control plane software stack. So there is an in-memory database where you create kind of the representation of the devices that have registered. That is through message and event handling. You see different quantum nodes, BSM nodes, measurement nodes, agents, web portals. And then within that, you have a kind of all different modules from resource orchestration to routing, to resource management, topology management, and all of that stuff. Something, if you are running a normal classical network, a lot of familiar things in there, but a lot of different things as well in there. Next slide. So what we're really trying to build is a modular software stack. And we're in this software stack, we're going to delineate orchestration, which is how you actually make the whole network work, with real-time control of the hardware. Now, if you ever have deployed optical networks, you know that there is a lot of real-time functions that exist within the hardware that communicate with each other devices. So the time-critical functions are in programmable logic. So FPGA is one great way to think of programmable logic, and the non-real-time functions run in CPU. And both of these are required in order to make this work, because there are time-critical functions and pulse-driven operations that need very real-time control. And then there is network-wide sync, calibration, automation, monitoring, resource, user-facing APIs that don't need that kind of a real-time control. Next slide. So one of the things that we started before designing is to provide a consistent network data model. Now we had to come up with that for the quantum network. So one of the opportunities I will talk about, and I'm saying that ahead of time, is do we come as this group and standardize the different properties and names? So for the system, we have properties like name, ID, control interface for different node types. We have got matter qubit information, what kind of gate operations is running, matter light interface, definitions of entanglement types, generation rate, qubit types, frequency, channels and channel type. So all of these were something that we developed internally in order to build the software stack to make it modular and scalable. Next slide. Again, I'm going to go quick because time is short, so you can always read the slides to get details of these elements. Now, one of the things is, how do you actually discover resources in this mechanism? So in this case, we have nodes that have control agents that register and send periodic updates. They talk about their features, and the controller or the centralized controller maintains the source of truth for the control domain. And the orchestration actually provides the comms between all the distributed components. So it does it through running a pub sub bus, a message queue, Remote procedure calls and write once, use everywhere schema. So that is how the orchestration layer works. Next slide. So one of the things that was really important to us is that we know that we don't understand everything, and they're all the people writing papers and producing new capabilities, whether it comes to routing, whether it comes to control, whether it comes to distillation algorithms or error correction. So we wanted to develop the software stack with actually modular so that anybody could write their own plugin. So you have a new component, you came up with a new idea, you write your own plugin and you drop it into the protocol stack and then you use it. But you don't have to develop the whole software stack from scratch. So the controller plugins define protocol logic, and this can be your own plugin. It can be the plugins that come with the software stack. The agent command interpreters drive hardware using hardware abstraction layer. So we did create a hardware abstraction layer because there are many qubit types and qubit platforms. So you can use NHAL to drive different kinds of stuff. Also, we kind of, you can write a hardware abstraction layer for a simulator. So you don't really need to have hardware in order to run the software stack. And then the controller exposes core functions like routing, scheduling, monitoring that can be used to compose, a workflow or a service or anything that you would like to see. Next. So the vision for this control plane, kind of just to summarize, is it is a framework for exploring the range of quantum network approaches. So it was not just built for our quantum network testbed, QuantNet, which I have presented before. So I'm not presenting that again for people that are listening to it for the first time. And again, you see a northbound API, a southbound API, a lot of pluggable modules in the center in the controller package, and then abstraction layer for real-time control to the hardware and hardware devices that we have in our network. We have quantum frequency converters, we have Bell state measurement devices, we have ion traps, but also for a simulation layer. So if you wanted to scale out or test the software in a scale-out manner, you would run a simulator with a lot of devices because it is currently very expensive to put a lot of devices together. And the hope is that this framework is just not useful for running your testbed, but it is an opportunity for the quantum network community to come together, to evolve together, to think about new standards, and basically tie in between the IETF work and all the testbed experimental works that are going on. Next slide. So what are the three things it provides? It provides software models for describing quantum resources, it provides plugin interfaces, and a hardware abstraction layer. And in the rest of time, I'm going to skip some. So if you can go to the next slide, if I have already talked. I will talk about this. So the way we design it is using async API. So there is a source of truth. There is consistent data formats. There is auto-generated objects that come from that source of truth and auto-generated documentation. So what I'm trying to say with this is we are following as current or best software engineering practices as possible in developing this. And it is not just a grad student put together kind of script that makes this happen. Next. This just talks about the resource models. Let's skip it. Next. And then, I think something we talked about. So there is a shared message bus that allows communication facilities using a schema, the controller plugins for routing, scheduling protocols, and any other plugin that you may want to pull up. And then for the agents which are running on the hardware or interacting with the hardware, there are command interpreters and abstraction layers that we use. Now, we have only defined that for the ion traps and the BSM nodes that we are using, but that also can be extended to whatever hardware devices that you might have in your lab. Next slide. I think more about the message bus. People can read it offline. Next slide. I think, again, next slide. I'm just giving some time for questions. So again, this is an example of the core routing plugin that we have. So we develop paths over a discovered control plane topology. Because each of the elements register, we get to know how they are connected, and then we are able to do routing between them. Now, because of entanglement generation, you may have constraints, like you may need a Bell state analyzer along the shortest path in the middle, and depending on what your whether you have a entanglement photon source in the middle, how do you reason about that? So this routing plugin allows all these different combinations to happen. Next slide. One of the things we presented in QCE in September, and basically the team got a Best Paper Award, was the two-level scheduler. So this two-level scheduler or course scheduling plugin is also implemented and available with the software stack that allows you to select time slots, run calibration, automated calibration operations, as well as set up connections end-to-end, especially if you have a long chain that you're trying to set, bring entanglement. This scheme really helps you coordinate all the nodes so that you can exchange the right information to set up this time. And those time slots, all those nodes are focused on getting that entanglement to happen. And this allows, so as I said on the other bullet, allows for automatic cycling between operational, like setting up entanglement, and calibration, because when you're out of calibration, you don't want a student to be running around trying to calibrate your test bed. This needs to be done automatically. Next. This thing is about the hardware abstractions layers, about how the agent command interpreters, which are connected to the hardware, behave and how they talk to the hardware. Next. Okay, so this is kind of important. So the device classes that we have for the hardware abstraction layer right now is a light source, a filter, light measurement, signal measurement, analog controller, digital controller. And again, this may vary for you. And the way we have built the hardware abstraction layer is something that you can add to it and enhance it. So again, I think I'm talking more about the architecture of the software than exact software itself. We have done experiments, at least at OFC this year, and again shown at the two-level framework paper, that we can use the software stack to actually generate entanglement using a user command, automatically start collaborations, automatically do bell state measurements. So all of them has been demonstrated for the IETF. We're just talking about the software stack architecture. Next. This is some kind of a requester lifecycle. So talking about workflows. So a user can submit an API request saying, I need an entanglement for this purpose. The request is validated and processed in the controller. Resource routing, pathfinding happens. The binding happens. Okay, we are going to use these devices. The scheduling, the two-level scheduler in finding the right time slot to trigger this request is done so that all nodes are available. You execute that, and then you collect results that you may then use for your paper. So that's kind of the flow. The software, next slide. Yes, that's fine. Time, I'm watching the time too. So software deployment. So we make it easy for you. So the software update pipelines will, automatically create container images and stuff that you can deploy. So all the tooling is there in order for you to use the software stack and deploy it. Next. So again, that's my last big slide. So IETF is about rough consensus and running code. So what we're talking about is we have a software framework to ease the running code piece of the rough consensus. The rough consensus still needs to happen. We're open to quantum network testbeds to collaborate with them to see if this is useful, to extend the software to make sure that it works on their testbed, and to implement the unique ideas as plugins and validate it either using simulation or testbeds. And the whole goal is to ease the development of code and testing of new ideas by this community as we move forward. Thank you. A couple of minutes for questions.
All right. Thanks, Inder. I don't see anybody in the queue yet, but we have about 2 minutes for questions if anybody's got a quick one. I see Dave coming to the mic, but Dave does not yet exist in the mic queue.
I went to the queue. I hit the join queue.
Now I see you.
Oh, okay.
All right, Dave Oran.
So if you put up like the previous slide that showed the workflow.
Yeah. Go back one slide. No, one more. Yeah.
More.
Yes.
Yeah. So the API that's at the top seems to come from a person. When we really want to run this stuff, the thing at the top of the API is going to be a quantum computer, right?
Yes.
So how do you extend the timing that you're trying to do all these scheduling computation and match it up with the timing that's going on when you're doing computations inside one of the quantum computers?
So that is work in progress. I think it's a great question. I think for now, we tested it using a human, so that's why we drew human in the picture. But you're absolutely right, that's not the end goal of the API. And that is one of the challenges that we are tackling right now as we integrate with a compiler.
All right, Robert, we got a minute and 15 seconds. Robert Broberg.
A quick question. Very nice talk. Thank you. A lot of neat work there. What does this run on top of? I mean, what's the transport? Is that, I mean, are you doing
I mean, for
that?
the non-real time, it's TCP/IP.
It is,
The
12
yeah.
TCP.
Yeah.
In what I think literary people would call foreshadowing, I've got a question for them later, but are you using some sort of schema or some sort of middleware for packaging your software, your data values, or is this actually straight up binary encoded data values in your messages?
I think right now it is. I don't know for sure. Let me get back to you on that.
All right. Wenji or Ezra would probably know. All right. I think we're done with that one. Wenji, thank you, Inder.
I can start the slide share. Which one is it? It's QuantNet or?
Should be next. Yeah. QuantNet controller. Right?
Yeah, I've already looked at this one.
I just plugged that in, but I haven't actually tried it. Was that
So,
what I was supposed to record?
You go ahead and get started.
It's
Hang
not
on,
this one.
try
It's
the
not.
clicker.
Can we try this clicker now?
No, this is not this one.
Oh, wait.
This is not slide.
Yeah, it isn't. So hold on just a second. Yeah, now the clicker is working, but now
Okay,
we need to do the right slides. Thank
you.
Thank you. Here, all set.
They should
So
be in
which one
order.
is it? Now I think it reordered. It's this one. Come on, wake up. We go ahead and give you the clicker.
You got to click the confirm your
Oh,
selection
I gotta
button.
click confirm. Okay.
Yeah.
Yeah,
that
I
should
was
be
just
there.
making it harder.
Let me see.
There we go. Okay.
How to
Great.
click
Yeah, there you go. You got it now.
this one? Click.
Yes. Forward and back.
Okay, so good morning. Welcome to these sessions, and I'm Wenji from Berkeley Lab. And first, thanks the Rod and the Wojciech invited me to be here. And the title of my talk is the design and implementation of real-time control of trapped ion quantum networks. And I got 15 minutes and 25 slides. So some of the slides won't go to details. So this is my talk agenda. First, give some backgrounds and the motivation why we do the real-time control of trapped ion quantum networks. Then we talk about what's the challenges. Then next, I talk about our approach afterwards and conclude our talk. So what is the quantum network good for? We know the quantum network eventually provide new capabilities not cannot be provided by classical networks. So the new capabilities range from the secure communications and the sensing and the scalable quantum computings. And over the quantum networks are being actively researched worldwide across different physics and platforms, including the superconducting circuits, nitrogen vacancy center in diamond, and the neutral atoms, and trapped ions. So this year's and the Nobel Prize award for the superconducting works. There are some good neutral atoms work from the Harvard, from the QIRG, and for the trapped ions, and from Oxford and Innsbruck. And trapped ion are one of the leading platforms for the quantum networkings. It has excellent quantum information processing capabilities. It provides the identical qubits with the long coherence time. The latest coherence time exceeds 1 second or more. And also it provides the high fidelity gates and the qubit state preparations and the measurement. And you see the single qubit gates go to 9949. And the 2 qubits fidelity recently, 2 weeks ago, last week, 2 weeks ago, and IonQ announced and it's 4 nice levels already. And the state preparations and the measurement is also very good. Secondly, and the trapped ion provided the inherent support for entanglement generation and distribution and the storage. It has the excellent and light matter interfaces, and this is Innsbruck has demonstrated very good work there. And it's trapped ion are perfect candidates for high fidelity fail state measurement because they are inherently identical, so they generate photons and has the spectral indistinguishabilities that's needed for the BSMs. And also it has provided the idea, it's a trapped ion ideal candidate for the entanglement storage because had long coherence time. If once generate entanglement, they can very good storage. Then now I gave a quick and overview of the state-of-art trip-ion quantum networking, and several building blocks of trip-ion quantum networking has been demonstrated in the lab. The first one is on-demand and coherent light matter interface for the trip-ion quantum networking. That's provided by the conducted by the Innsbruck. Then, and also they work on the high performance and high fidelity QFC, quantum frequency conversion from the photon from the trapped ion goes to telecom bandwidth. And also the Nanians group and have the quantum repeaters. And secondly, and the high performance, high rate and high fidelity remote entanglement between the trapped ion over long distance has been demonstrated in the lab. So recently you will see the work from the Innsbruck and from Oxford, and so all this very nice work. Then to moving this experiment from the lab environment to the field deployment, we need not only the fundamental advance in the quantum science and the quantum technology, but also need efforts in quantum engineering, need engineering of quantum networks. One of such effort is the real-time control of the quantum networks. And so for the what are the challenges are? The first one, that we need the control qubits on the order of microseconds and or less, while protecting them from the environment, the noise. Why is that? Because we just mentioned the coherence time is exceed 1 second, but we need to control at the microseconds level, because some of the physical process and the for the quantum information processing occur at the microseconds level. So your control must be conducted at that level or at that scale or less. So to ensure the proper operations, and also for the control and manipulation, quantum state are sensitive to noise at a single atoms level. So the control and the manipulation of the qubits and the ions in the real network environment is really challenging. We need to protect them from the noise. The next one is the need to run entanglement generation on the order of hundreds of microseconds or less. That's because as the size of quantum network get bigger, and the photon loss and the communication overhead is get bigger, and constrain the ion entanglement generation rate. So you want to try and attempt the repeater rate as higher and higher, so then we can have the good end-to-end entanglement generation rate. The third one is need to control and the synchronization in frequency, time, and polarization phase and or their combination, because high fidelity BSN need in the temporal spectral and frequency polarizations indistinguishabilities. And as the network get bigger, and synchronization control is getting more complicated. And we over the last 20 to 30 years, in telecom has very good and synchronization controls, but most of these synchronization control move to the quantum network. They need significant improvement. So the synchronization control is a challenge. The last one is, of course, and we need to design and implement our software modular and scalable and make it extensible. So here is our approach. We built a trapped ion quantum network testbed in Berkeley and the QuantumNet testbed, and we design and implement two-level control framework for the testbed, and a real-time control software for the trapped ion quantum networks has been designed and developed. So. And this is the QuantumNet project, and Inder just gave the talk, and he's the PI for this project. 5 years project with the Berkeley, with the Berkeley lab, UC Berkeley, Caltech, and Innsbruck. The project goal is, and two goals. First, in hardware, and we develop a 3 nodes testbed, and to demonstrate the basic capability of a quantum repeater and the distributed quantum computing. In software is architecture and the product stack, and that's like we do in the classical network. And that's a research team. And now I start to talk about our real-time control system design and architecture. So the first one is, the first question we need to address is real-time control in how we do the real-time control in the distributed environment. Our strategy is impose the hard real-time constraints at the lowest level, and we a systematic approach to meet the constraints. First, and we time critical functions running on the dedicated and RTIC systems, and the data control and the communication channels and established between the related entities, and non-real-time functions implemented in the CPUs, non-real-time communication implemented through the TCP/IP. And we develop a two-level control framework. You will see at the network level, and we have logical centralized server control, organize the everything. And the node level is dedicated hardware systems, like we use RTIC to do the node level real-time control, and the dedicated link and for the real-time control and the communications. And this is slides illustrate the node level controls, and you will see the triplan-based and quantum node, and you'll see the RTIC, and everything is there. And the right hand the figures is the RTIC-based BSM node and do the bell state measurement. All these things is using RTIC. And next, this one is a closer look at the RTIC-based quantum nodes, and you will see and the quantum server and not quantum server, sorry, is the RTIC server, and also include several the FPGA card at the command of the server, and the FPGA card to do the real-time controls, do the RF control, DC control, ADC control, TTL controls, and etc. Next, and we for the two-level controller, and we develop our scheduler. The scheduler to do the synchronous time slot scheduling, and it supports the synchronized operation in a distributed environment, because we are distributed network. Sometimes the function we need to start simultaneously, and also it supports the calibration and the work, because we need to periodically calibrate your node, calibrate your lasers, calibrate your fibers. Here is now we talk about the real-time control software, and this is the software because the quantum operations on the ion and the qubits correspond to the tailored pulse and the signal control signal. You see the diagrams, you will see that's for the control sequence for the Robbie flopping experiment. And we designed our real-time software in the modular ways, and we develop a list of the core building block, and this building block can be combined in a flexible ways to build up more complex functions. And also the real-time software supported repeated and execution scans and calibration. That's a lot of work in the quantum network. You laser calibrations and you frequency calibrations, magnitude the laser magnitude calibrations. So here is you see the right hand side the figures and the building block, and we compose it to the more complex function, then load into the RTIC output the control sequence and for the functions. Here is the software implementations we using the Pythons. So and that's something there. And then we evaluate our software in our test bed for the functionality, modularity, and the reusabilities. So this is, we just recently conduct this work in the test bed. And here is some preliminary results for the collaborations. And here actually is one is for the frequency, another is for, or this is one, another is for the power. So that's and this is coherent operations, and one is for the Robbie oscillation. Another is for Ramsey oscillations, and we're using our software to generate a control sequence. And this result shows and our control system and the software works very well. And here is the conclusion, the discussions, and the result shows and the system and the software and address the challenges we listed earlier, and that's the initial test. And then the control software be designed, implemented in a modular levels, and be combined and composed to implement more complex functions. And this and the real-time control software can be scheduled by the two-level schedulers and in the automatic manner to schedule the functions. And we have demonstrated in the OFC in these years. And here is a few questions. I have 2 minutes. And the first, the questions to the research community and the standardization community. The first, what are the major challenges need to be addressed to move quantum network from the physical experiment and to the field deployment? The second one was the basic building block and for quantum network. that need to be standardizations from the architecture and the controls perspective. The last one is, and because I myself do the research, do the controls, and you do the real-time control and the non-real-time control, right? You look at the Linux TCP/IP, right? And you look at the source code, and it really clear, you understand what's the non-real-time control part. And then from Ethernet and the driver go to driver still is non-real-time control, but once the driver, the interface is to the Ethernet, and the Ethernet, the card that goes to the real-time control. So for the quantum network, if there's a demarcation lines and between the non-real-time and real-time, so where it should be drawn, and similar to what we did for the TCP/IP process. So that's my talk, and I have 1.5 minutes for the question. Sorry.
All right. We'll take one quick question, but it's got to be a quick one. Robert,
A question for that I see the RTIC, I'm not very familiar with it. How do you do the distributed synchronization? How do you do the distributed synchronization? I mean, I see that LBNL link, right? The several kilometers. How do we know the clocks are
the high level synchronization is not through the RTIC, it's through the control system at both sides. The RTIC is do the output of the pulse, but synchronization for example, for the frequency, right? And we use the URE cavity, and we have 2 URE cavity, both sides calibrate and lock to the URE cavities. Then we have the dedicated synchronization link, and they have fiber. They're not through the RTIC. And also to time synchronization. Time synchronization is not important in our case. Frequency synchronization is more important in us. We have the 20 microseconds wave packets, and the frequencies fluctuation we need to control under 100 hertz. So that's the tough part. We have the URE cavity. That's
all right, yeah.
Yeah.
So sorry, Diego, we're going to have to move on. So sorry, you won't get your question in. I had booted Robert out of the queue a little earlier, so that was why I went ahead and went with his question. All right, thank Wenji. So let's see, who's up next? I think Joaquin's up next.
I can hold on. I need to take them back. Yeah. Look. Yes. Stop slides. Start slides.
Okay, you doing it.
Which is this? This is
Should be the next one down. Yeah.
Yeah.
Confirm your selection.
Ah, great. Click harder.
Yep.
Yes. Okay.
All right. Next up is Joaquin Jung.
All right. Thanks for having me. I'm Joaquin Chung, research scientist at Argonne National Lab and the University of Chicago. And today I'm going to talk to you about our project that we call InterQNet, which is a heterogeneous full-stack approach to co-designing scalable quantum networks. So just to tell you a little bit of background on InterQNet, our goal is to advance the state-of-the-art in scalable quantum communications. And we take like a two-pronged approach here with 2 thrusts, if we want to call it like that. InterQNet Achieve is the practical realization of a full-stack heterogeneous quantum network. And InterQNet Scale is a system study of scalable quantum network architectures. And there in the bottom in blue, I have an archive paper that we published recently that summarizes the InterQNet project and our most recent results. So for InterQNet Achieve, we are developing a campus scale testbed at Argonne National Lab that includes 3 different qubit platform devices. One is ytterbium atoms, erbium ions, and the other is superconducting qubits. And the goal of InterQNet Achieve is to distribute entanglement between erbium and superconducting qubits using ytterbium as a quantum repeater, as a prototype of a quantum repeater. And these will all be over telecom fibers deployed at Argonne. And we will need frequency conversion because all these qubits are in different wavelengths or different wavelengths. And we also want to do all that automatically, as in there, and Wenji already greatly articulated. If we want a network control, this all needs to be automated to move from physics experiment into quantum networks. So yeah, this is just a map of the interQNet, the Argon Quantum Network is a 5-node campus scale network with a partial mesh topology. All the links are under 5 kilometers. We have 2 nodes. The location of the, you can see the location of the qubits, and then we also have hubs that have connections to other institutions in the greater Chicago area. Then for interQNet scale, which is our system study, we will use mainly simulations and theory. But in here, we will look at like what are the architectural design choices that we can make when we want to scale to a quantum internet. So we can think about centralized control, which is good for small scale and these near-term quantum networks. But then do we need distributed control? We can look at in-band or out-of-band signaling. So there are many choices that we are exploring here. But for the rest of the talk, I want to just tell you about 2 recent works from interQNet scale. The first one is the design and simulation of the adaptive continuous entanglement generation protocol. This work was presented at the QCNC conference early in April in Nara, Japan. And just to give you a little bit of the introduction. So the goal of quantum networks in general terms is to distribute entanglement between 2 users, Alice and Bob. And then state of the art tells us that we have to find the path between Alice and Bob, generate link entanglement, schedule swapping operations, and do purification either at the link level or at the end. But these may take time because all these processes are probabilistic. So we want to reduce the time to generate this end-to-end remote entanglement that users have requested. So we ask the question, can we continuously generate entanglements between neighboring nodes independent of the user request? And then can we design a protocol or adaptive scheme that can guide the selection of these neighbors in a smarter way, knowing the past user request? So I don't know if this has a pointer. Here, okay. So yeah, in this figure in the left, you see that I can decide to just generate entanglement with all my neighbors with equal probability. But if I am smarter, I know that these 2 neighbors are the most popular requests that I'm receiving. So I will just focus the link entanglement generation to those 2. So we designed our protocol using finite state machine. I invite you to find the paper, and I'm not going to spend time explaining that. And then we implemented that on Sequence, which is a discrete event simulator of quantum networks that we have also developed in our group. Here you can see the software architecture of Sequence. And then all the boxes in yellow are the ones that we extended to support the ACP protocol. And ACP had to run outside of the software stack because it was something that doesn't fit in any of the boxes there. So I'm just going to flash the simulation setup, but the things that I want to mention here is the request arrival rate was, 10 hertz, and link distances of 10 kilometers. We were using telecom fiber attenuation to 0.2 dB per kilometer. And then we run a lot of simulations in this, but I just want to highlight the large scale one. So we tested this in a 200 node autonomous system network topology, and we evaluated 3 protocols. The one that we call our ACP, which is the one in red. On demand only, ODO, which is the one in blue, that's state of the art. As soon as I receive a request, I start generating local entanglement, try to do the swaps and all that. And then UCP in green is the uniform continuous protocol. So in this one, I'm just generating entanglement with all my neighbors, regardless of what are the requests I always generate. So you can clearly see in the plots, and my two figures of merit are the time to serve and the fidelity of the final entangled generated pair. So you can see for both ACP improve time to serve. You can see how it drops from 12 milliseconds to just a regular 8 point something. And then the other two stay flat. UCP fetch you a little bit of improvement, but it's not greater compared to just doing the state of the art. And then just to keep things interesting, we changed our traffic matrix. So by traffic matrix was how the requests were being scheduled, requested between different users in the network. So in the middle of the simulation, we just changed the complete pattern. And you can see how ACP shoots up time to serve and drops fidelity, but immediately catch up and maintains good numbers. So that was for ACP. Now I want to tell you a little bit about the demonstration of remote entanglement distribution across a campus scale quantum network testbed. This one uses, so just to remind you, the goal of InterQNet Achieve is to do this heterogeneous entanglement between 3 different qubit platforms. So we use a plane abstraction just to organize what are we gonna do. So we have infrastructure plane in the bottom. That's where we have all of our devices in a control plane. We will have this look very similar to what Inder presented in the morning. So I think we're converging into like what should be the abstractions and the type of services that should be provided. So in the top, we have a service plane that for us could be entanglement distribution or quantum teleportation. And then we have interfaces to the users. That was northbound interface in Inder's presentation. So in this prototype, we implemented agents for all of our devices. So these agents will control entangled photon sources, SNSPDs, our all optical switches, and the time taggers. Time taggers are the ones that collect information from the SNSPDs. We also build our own clock synchronization system using RF over fiber. Communication between the agents and our orchestrator is over gRPC. And then the orchestrator is centralized and it can schedule, not schedule as rigorously and as Wenji explained in his previous talk, but it can trigger automated calibration and continuous operation. So in here we evaluated, because we had just entangled photon source and our qubits from InterQNet are not ready to be connected to the network yet. We were using a commercial entangled photon source, so we measured 2-photon interference and quantum state tomography. And the results show that we obtain a very good fringe visibility, approximately 95%, that you can see in the plots in the bottom. The schematic here is the testbed that we use with 3 different sites, like nothing is collocated, no spool of fiber, or everything is remote. And then just for fun, we ran a long run experiment in which we measure fringe visibility and we were continuously rescheduling the same experiment over 12 hours. And the idea was to trigger, if the fringe visibility was dropping below a threshold, we will trigger polarization drift compensation. Just because we are fortunate but unlucky for the experiment, our network is too stable, so polarization drift compensation only trigger once. And I think that's all I had.
All right.
Thank you.
Thank you, Joaquin. We do have a couple of minutes for questions. Dave Oland's first in the queue up.
Might take you a second back to this slide. It's the simulation slide that had the little box at the bottom with the simulation parameters.
Yeah, absolutely.
So you're showing results for that set of simulation parameters.
Yes, sir.
What others did you try? So for example, you've got 2-second decoherence time, which seems, optimistic at best.
Yeah.
And then you compare the protocols. So did you try other settings to see whether the protocols differ as much when these simulation parameters change?
Not really, because we were assuming. Yeah, we were.
I want to make sure you're not cherry picking here, right?
No, we were first comparing against the state of the art. So we gave the same network parameters to everyone. We could extend this easily to like changing fidelities or adding more noise to the network. Of course, we won't scale
2
to a 200.
seconds seems to be well beyond the state of the art.
I think Wenji mentioned that
He's
ion
got
traps
close
are
to 1 second, yeah.
like, yeah, we're like putting like, okay, optimistically, let's hope that we can reach. No, I mean, sorry.
I don't want to push back. It just seems like some of these other simpler protocols, for example, the one that does continuous generation, might actually wind up doing better if the coherence time is shorter, right? Because you're guaranteed to have like a fixed, font of entangled photons coming at you quickly enough to be able to execute the rest of the protocol. Right?
You mean you mean increasing the entanglement generation rate, or
either that, or if the decoherence time comes down, right, you have less time to make use of a less uniform generation.
But if they decohere, then you are going to lose them, and then you are not going to deliver anything.
Take it offline. Thank you.
Okay.
Yeah. All right. Thanks, Joaquin. Let's go on to the next talk. Next speaker should be, let's see, I don't have the queue open in front of the agenda open in front of me.
Yeah, coming up.
And the
Stop
agenda
slides.
is, I think Leonardo's next, yes. So next speaker is Leonardo Bacciatini.
And here's the clicker.
Oh, yeah.
And now it should even work.
All right.
All right. You have 15 minutes as well, including Q&A.
All right. Hi, everyone. I'm Leonardo, and I'm a postdoc at UMass Amherst, working with Professor Tasley, Vardoyan, and Stefan Krastanov. And today I'm going to talk about our line of work on connectionless quantum networks. So let's delve into it. It's not
Clicking, not working.
there you go. Yeah. So the goal of a quantum network, as we know, is to distribute entangled states to end users that can then use those entangled states as consumable resources for their applications, for example, distributed quantum computing, etc. We are going to focus on two-way quantum networks for this talk. So the idea is that first, we can distribute entanglement locally on physical links. And one thing I want to point out now that's going to be very useful later on in this talk is that typically we can trade off the rate with which we generate entanglement over the links and the quality of those entangled states. And that spans from hardware considerations. For example, we can tune the pump power of an SPDC source, or we can tune the brightness of an emitter, but also from logical considerations. For example, if we apply distillation, we reduce the entanglement generation rate, but we also increase the fidelity. So this is going to be useful later on. So this is probabilistic. So we're going to get some links, entangled links on the network, and then we can use, if we have a path connecting to end nodes, what we can do, we can apply local measurements, and the clicker is now working again. There you go. Sorry.
Yeah, don't point it at the screen,
Oh,
we're over here, but I'm
that's-
not sure, I'm not sure if
yeah.
that's what's making the difference or
That's
not.
very fair observations. So yeah, and then we can perform local operations at the intermediate nodes called swaps. And what we get at the end is an end-to-end entangled pair between the end nodes. So this is the setup we're working with. Now, first of all, let me define what I mean by connectionless. So connectionless network in general, I define it as an application in a network where we do not keep state at intermediate nodes. So we keep them as simple as possible, and possibly we treat every application request separately. So there is no hard resource reservation in terms of long-term, at least. We do not reserve long-time resources for applications. Why would we want to go connectionless? So one very good advantage of connectionless architectures is that they allow for simple operations without having to synchronize more than 2 nodes at a time. So this might be very useful for a quantum network, especially because synchronization issues are very, very, very hard compelling. Also, they can, in connectionless network, they can lead to very high utilizations with respect, for example, to time-slotted architectures. Another reason is that it already proved winning. The internet is connectionless. Now, with this, I don't want to say that the internet is perfect. We have to be aware also of the drawbacks of the internet architecture and the fact that quantum networks are different inherently. But why not leveraging things that are successful in the internet for our purposes? But the question is now, how do we realize and design a connectionless architecture for two-ways quantum network? Like from the setup I described before, it seems hard to come up with a connectionless perspective. So the idea, the key that we pursued in our first work is using sequential swap schedules. So let's see what this is. So sequential swapping is pictured in that figure over there. And the idea is that to distribute entanglement between the 2 blue nodes, which are the end nodes, we perform entanglement swapping at each intermediate node 1 by 1. So we do not allow them to concurrently perform entanglement swapping, but we impose this kind of synchronization. So for example, we have a link level pair between the 2 nodes, blue and first white. Then we create the second one and we swap. Then we have an entangled pair between the first and the third node, and at that here, and that we create the last entangled pair and we swap, and at the end we have an end-to-end bell pair. Now, if you look at this, it really recalls a hope by hope movement of something, right? What happens is the entangled state gets longer as every swap occurs. So we can see this as if we were moving somewhat, like in an abstraction, some data. So we have actually a half of an entangled pair, so a qubit state that's being moved hope by hope towards the destination node. And at the same time, we have some classical data that's also moving hope by hope. And this classical data is required because at the very least, we need to transmit to one of the end nodes the BSM correction bits that are needed for entanglement swapping. But more than that, from like engineering considerations, we need, for example, the destination address to let every intermediate node know which is the node that we are going towards. So these 2 fields are, at the very least, have to be included. Now, if we group together these two concepts, quantum and classical components that are moving on the network, we can come up with this abstraction of a quantum datagram, which is, we can frame sequential swapping as the forwarding of quantum datagrams across the network. So the idea is that this quantum plus classical information attached that's moving, we call it a Q datagram, and the entanglement swapping operation corresponds to the forwarding of this virtualized packet. And if we switch focus to the whole network, now we can see the whole quantum network as a system that contains many traveling Q datagrams. Here I show between one end node pair, but in general, you might have multiple pairs of end nodes, right? So, it really recalls a packet switched system, right? Now, let me do the following consideration. Every Q datagram in the network maps to some qubit state stored inside the quantum memory. And we know from the classical internet that the highest the number of packets in the network, the highest the congestion will be, the highest the latency. And there is the direct mapping between latency in quantum networks and decoherence level experienced by distributed entangled states. So what I'm saying here is that we can address and control decoherence by managing the congestion level in the quantum network in terms of number of Q datagrams inside. Before moving on, let me just frame everything I said so far within a more structured architecture. So let me frame inside a protocol stack. So if we imagine a TCP/IP-like protocol stack for the quantum internet, we have a physical layer that takes care of quantum operation, a link layer that's something that we can imagine something like the ACP protocol described by Joaquin that takes care of distributing bell pairs on links. And then we have a network layer, which is what we have focused so far, that takes care of turning those link level bell pairs into end-to-end bell pairs. And this is where the connectionless perspective takes into place. And now, from now on, we're going to focus on the transport layer. So we just we switch to an end-to-end perspective, and we charge the end nodes with a task to monitor and control decoherence. So as on top of the connectionless architecture I just described, we install on the transport layer, so from just purely end-to-end perspective, without any intermediate switch involved, a TCP-like protocol for congestion control. And so what we call, for the purposes of this talk, we call it quantum TCP, and it basically manages decoherence via AIMD congestion control on the quantum network based on the number of Q datagrams in the system. And we compare it against a baseline protocol called AQTP that basically does the same thing, but with quantum memory reservation. So it's aware of the applications in the network, and it reserves to different applications subset of the quantum nodes' quantum memories to prevent congestion as a whole. And if we look at the plot, quantum TCP outperforms AQTP even if we give 4 times more quantum memories to all the devices in the network with AQTP. And this is because the connectionless perspective, we are able to treat every Q datagram by itself, and we're basically overbooking the links a little bit too. And we drastically increase the utilization of the network, while still maintaining the coherence under control. For example, if you are familiar with active queue management, we install a PI controller on the quantum network to keep the latency at every node under control, and that proved very, very effective on the results. Now, of course, we are talking about a quantum network, right? So a purely TCP-like protocol has nothing to do with quantum. So we can definitely do better. So let me just talk about what we did as an extension. Is why not using a quantum-informed protocol for managing the resource allocation in the quantum network within this architecture possibly, but it's even more general than that. For example, let's go back. You remember I mentioned this trade-off on the links that we can have between generation rate of entanglement and its quality. For example, we can tune the pump power of the SPDC sorts. Well, we came up with a protocol called Q-primal dual, that keeps, for example, this knob as an additional tool to manage the configuration of the network. And it's a fully distributed protocol. And you can see that if quantum TCP from the previous slide is the red baseline in the figure, and this is how much we gain in terms of secret key rate as a performance measure. So it's really major improvement, and it shows that there is a lot of margin of improvement when it comes to actually address quantum networks with quantum-specific tools, right? So we got a little bit of the benefit from both perspectives. We are exploiting good features of connectionless design, but we're also exploiting the properties of a quantum-specific resource reservation scheme. Now, about Q-primal dual, I will not go into detail, but it's very scalable, decentralized, and provably stable protocol for resource allocation in a quantum network. and it can really work well with the QDatagrams network layer that I showed you before. And I encourage you can find all the details in our paper here, and it's on the archive right now. We posted it very, very recently. And to conclude, let me just give a quick shout out to the simulator we've been using. We developed it at UMass. It's called Quantum Savory, and it's fully open source and based on the Julia programming language. It's highly modular. And we already implemented the whole architecture that I've talked to you about in this simulator. We have office hours every Friday, 12:30 East time. So if you want to join and have questions, you're free to stop by. You can also check the website and send us emails. We are happy to talk about it. We also have collaborations going on, for example, with Sequence. We are actively talking. And that's all from my side. Thanks.
All right, thanks, Leonardo. Questions? Anybody with any questions for our speaker? All right, Jonathan. I know sometimes it takes people a second to find the tool, to find the raise your hand button.
Yeah, I had the Microsoft Authenticator and I had to switch apps. So I'm sorry for the very naive questions, but I'm very new to this quantum computing and networking. So you're basically using traditional TCP and fiber networks to communicate between the nodes to synchronize the states and everything. And then you send the data using quantum qubits. Is that it?
So it's up to you to choose how you transmit classical data. But since here we are not decoupling control and data, like for example, it's you have entanglement between two nodes, and then you extend it. You want to extend it with the next swap. You have to be quick with how you reach that. So you could use TCP/IP to send that classical information to propagate to the next node, but you can also like choose something that leads to like faster time point. So it's up to you. It's really up to you to how to propagate classical information. The model is fully agnostic with respect to that. And the thing that putting together quantum and classical is purely an abstraction. They do not actually travel together. It's like we map the BSM operation, the measurement, and the propagation of classical information together within a virtual packet, but it's not actually what happens physically. So it's really up to you how you want to propagate classical information, depending on what leads to the latest latency possible. I think that's
thank you.
Key.
All right, with that, I think we should probably move on, and you can catch any of the speakers in the hallway after the session ends. Thank you, Leonardo. All right, so next up on the agenda is, let's see, I think Marcello's up next. Marcello Calefi. Should be deep leveraging internet principles, right? No, that was the design principles. Should be that. They are in order. It's just a little easy to get confused.
Okay.
Hang on just a sec. Let's see. Are you ready?
3,
Okay.
2, 1. I'm gonna take these 15 seconds.
No, go. Start going. It's fine.
Okay. But it's not working. Or okay.
There you go.
Just 5 seconds for the people that work with us, and then I have plenty of slides.
Stand close to the mic.
Yeah, and I have plenty of slides, and I have to move forward. So where are we? RFC 9340. It's not working. Okay,
Yeah, it's just a little laggy.
Okay, so we'll keep going. So this is what we have in the RFC. I can watch over there. And to achieve this goal, a quantum network stack should be built from the ground. This is in the abstract, from the ground. According to which principles? So today was everything about quantum control plane. You can have different dimensions of quantum control plane. A dimension dealing with testbed, which mainly deals with the synchronization, classical signaling, and so on. But you may also have a long-term perspective on control plane. And it's not moving up.
There you go.
Okay. Can we use classical internet principles? Well, we have two drawbacks. First drawback has been around for 25 years. That picture is from 2001, IETF 51. We have ossified protocols, and we were not able to fix the ossification of the protocol stack, well, because it's very big issue to change protocols all over internet, okay? So we have issues with current TCP/IP protocol stack. And we decide, okay, let's keep like this because no one wants to deal with the enormous effort of changing protocols and protocol stack and principle. But we have a second drawback. And the second drawback is due to how current classical internet has been built. Two are the main principles. First principle is simplicity principle. Keep it simple. And the second principle is the end-to-end argument. And the end-to-end argument has been bring up. Why? Well, because classical forwarding is stateless. And so if you have a stateless resource, you should keep the complexity over the edges and have the core of the network simple. Now, what's the deal with quantum internet? Well, the problem is that entanglement is stateful. It's not stateless. And I think I have to click twice. And the problem, okay, here you have a picture, a table from between the difference between classical information, quantum information, and entanglement. Entanglement is not quantum information. Entanglement is a different resource. And the issue is that entanglement is stateful. So if you try to map end-to-end principle together with entanglement, then you will have, okay, an issue with the simplicity principle, because you will try to map stateful with a internet architecture which has been designed for stateless resources. And so we finally, after 40 years, we have the possibility of redesigning an internet architecture by choosing new design principles. And so we have two different possibilities. It's really, okay. We can stick with classical internet philosophy, end-to-end argument, or we can try to find new design principles which better maps with the quantumness that we finally have in the quantum internet. And of course, this is a radical departure from TCP/IP. And since at least a couple or three IETF meetings, we are trying to bring this to the table. Okay, so principle in practice. Couple of years or 1.5 years, we have this talk. I think we were in Prague, and we start saying, well, can we bring quantumness within the network so that we can redesign network functionalities so that these functionalities operate better than classical functionalities that we have? And in a recent paper, we came out with this idea. And this idea actually fits very well with internet principle, because here you have a famous sentence from RFC 1958, and which is the principle of constant change. So we have the option, the possibility of changing our principles, our philosophy, and we should take it. And in my group, we are trying to take it by exploiting quantumness also for the design of network functionalities. This is the main catching argument here. And okay, so we are thinking about moving from packet switching to entanglement switching. Why? Well, because we don't want to transmit quantum information. That's not the task of an entangled network. The task of an entangled network is to entangle nodes. And you want to manipulate that entanglement so that some application, which we don't know yet which will be able to distribute quantum information, maybe also classical information. But the overall goal has been changed since the recognizing of entanglement as key resource. We don't want to forward packets. This is not what quantum networks are. Quantum networks are all about entangling. And still, okay, we are thinking that maybe having this very light core network where all the intelligence is at the edges doesn't fit with entanglement. And indeed, our community is, every time that tries to reconciliate entanglement with classical TCP/IP layering, somehow has these issues. There have been at least 3 or 4 attempts. We reviewed that attempts, we discussed that attempts. So why can't we switch from intelligence to the border to like circuit switching intelligence within the network? And the rationale is because entanglement is stateful. And so we may have a control plane and a data plane where the control plane is about entangling nodes and managing entanglement, whereas the data plane is about forwarding entanglement. But here forwarding should be taken with a particular attention because we are not forwarding information. We are distributing correlations, so the task has been different. And we start trying to identify 2 main entities. The one on the control plane is the ESP, the entanglement service provider. Those are the key nodes which distribute, or better, which generate and distribute entanglement. And if you look at those lights coming from the testbed, you will feel that the synchronization, the controlling, the distribution of entanglement is not an easy task. And we don't think that will be easier in the future years. It's something that requires a lot of coordination, especially when you have multi-part entanglement. And then we have the entanglement-defined controller, like in classical networks. Okay. And so we try to have this centralized architecture, and we want to have a quantum native control plane. Now, what is control plane? Okay, let's go to the book. We have Gross-Ross, right? We have these books which have been there for 40 years and nothing changing in the last 40 years. And the implicit assumption is that there is classical connectivity. So you have a name, an address, and a route, and your job is to forward packets closer to the destination, because there is only one destination in the network. There is only one node which benefits from that packets. And the routers forward packet just as a service to the network, but the forwarders of the packet, they cannot exploit that information. That information is not meant from them. And existing proposals on quantum control plane are following the same underlying implicit assumption. Connectivity is more or less static in the sense of network dynamics. And you have that connectivity, you search for a pattern, then you entangle, and then you forward the destination. What are the drawbacks of this approach? Bottleneck to scalability, because entanglement has dynamics with order of magnitudes way shorter than classical networks. You consume entanglement. It's not like a route. You have these resources which are depleted upon use. And then you have suboptimality. Why suboptimality? 2 reasons. I would say quick reasoning. You are not exploiting the connectivity enabled by entanglement. Entanglement allows you to have nodes which are far in the physical topology to become close in the network overlay. Entanglement redefines the concept of neighborhood. A neighborhood is the fundamental concept underlying IP addressing. That's the shorter drawback. The long-term drawback is that we are stuck to use classical network functionalities to drive a quantum network. Now, let me make this example. It's like having a quantum computers trying to solve integer factorization with exhaustive search. We have quantumness, and we decide to not exploit by mimicking classical principle and philosophy. This is something that bothered our group since the beginning. So we were, you remember, in Prague trying to propose this quantum native control plane, which you have mainly, the main novel of this quantum native control plane is the fundamental functionality of a network, addressing. So we want to switch from a classical addressing to a quantum network addresses. And I'm run out of time. And you have, of course, you keep having a classical IP addresses. You need to distribute classical signaling. You have that for free, so we are not saying we want to switch down classical internet. But since we have qubits in every node and we have entanglement, why can't we have a quantum network address? And why can't we have a quantum header? And the quantum header is responsible for implementing the control plane, while the quantum payload is responsible for distributing entanglement, for entanglement nodes. And we will have a quantum routing table as well. And we were trying to find case for this quantum network address to bring to our community, right? And I'm a routing guy, so everything in my early career was about scalability. And there is this very well established area in classical networking, which is compact routing, okay? The overall goal of compact routing is to have sublinear routing tables with sublinear network addresses and with a path stretch. Path stretch is the suboptimality of ignorance, bounded by a fixed factor in any network regardless of the priorities. And in classical network, usually you have compact routing, which is still based on location-dependent addresses. You compact nodes in a set of nodes by assuming that they are close to each other. So thanks to the quantum addressing, we were able to have the first fully name-independent compact routing, able to achieve a good entangling stretch, either 3 or 5, depending on whether you have most of the nodes dealing with long links or just a few subset. And that's it. And actually, not that's it. In order to have subset of nodes sharing the same address regardless of their location, we had to come out with a new oracle for the sharing, a new oracle for Grover search algorithm, but that's all in details. So what we try to say here is that we may start investigating quantum networks, not just as networks trying to deliver quantum message with classical functionalities, but quantum native networks where quantumness is also in the network functionalities. And we are trying here also to have some call for interest in updating the RFC 9340, because quantum control plane in that RFC is explicitly declared as out of topic. So we would like to see if the community is interested in working on this. We have just already a couple of interests, and we are open to collaborate with all of you. Okay.
Thank you very much.
All right. Thank you. And I think we're actually out of time. We're over time here a little bit. So catch Marcello in the hallway if you want to ask him questions. All right. Let's see. And our next speaker, Roger Selly, is remote.
Hello, can you hear me?
Yeah. Hang on just a second. All right. Let's see.
You should have slides control now.
You should have slide control now.
It looks like it. Thank you very much. Thank you very much, Rod, for
your voice is a little on the loud side just in the room, and we don't have an audio engineer in here, so if you can keep it just a little lower, that would be good.
Okay, how about that?
That's perfect.
Okay, good. Thank you so much, Rod, for organizing this and allowing me to present quantum tomography, teleportation, and distributed quantum computing. My name is Roger Selly from Panvia Future Technologies. So the goal is distributed quantum computing. And why? Because we think we can build scalable, large scalable quantum computers using many distributed quantum computers linking together. The way to do this is with quantum tomography. That's the piece that I'm going to be talking about today. And teleportation is the actual example of how this works I'm going to run through. And the audience is really intended to be kind of software developers who would like an API for this quantum.
Roger, are you still on your title slide?
Yeah.
Okay, good. Just making sure.
Yeah. So now here is the agenda for, we're going to introduce the quantum possibility space, which is a way of describing the quantum tomography, how it can be put into JSON, JavaScript, object notation. And then we're going to run through the teleportation example as a hands-on way and visualizing how the state probabilities change gate by gate. The result is going to be, we're going to, after showing the different combinations, we extract a formula and qubit functionality for Brazard's teleportation as a quantum computation. And then we're going to show how this could be web-based. Next, we're going to go into how the QPS could be used in quantum key distribution to distribute actually many qubits. And then ending up with a more dynamic picture of what happens when you actually want to measure and collapse a QPS. How does that work? How does the QPS evolve once you actually collapse one of the qubits? Okay, next slide. So this is the quantum possibility space. It is really a simple concept where we have a list of non-negative integers and a complex magnitude. So these represent wave functions where the non-negative integer is the state vector of each wave function, and the complex magnitude is its magnitude that can be used in quantum gate operations. And the multi-qubit state vector is defined by the one states of each qubit raised to the power 2 to the power of the actual qubit number. So we end up with a multi-qubit state vector, and this is in little endian order. So you have the qubit 0 here, and it reflects a binary, conventional binary. So basically we have a quantum possibility is a new possibility space, a new way to compactly, accurately represent quantum tomography, the composite state vectors and complex magnitudes that define wave functions of the multi-qubit entangled state. So as a practical example here, we've showing the QPS encoders as JSON, and we got 3 different circuits here, each comprising 3 qubits. We have various state vectors and their associated complex magnitude. And these all, the squares of all these add up to 1, as you would expect. And in each case, we've got a qubit index and a label that is associated with that qubit. Okay, next, this is Gilles Brassard's quantum teleportation as a quantum computation circuit in his 96 paper. And this is showing how we store the qubits, we connect them into into a multiverse structure where the state vectors in each circuit are represented by those complex numbers. And then we manipulate them through these quantum gates, and end up with a output Alice state where all of the purpose of this circuit is to ambiguate all of the qubits, so that you look at each qubit is going to be in a 50-50 superposition as the output of this circuit. So next slide, I'm going to show the first half of that circuit in operation. So what we have here is the state probabilities by state vector in color coded. So we can, this is set up with, we've got 41 different circuits here running in parallel, and each has been fed different inputs of Alice's qubits so that we can examine how the state varies in each case. So we've got a pattern here where the top 5 circuits are going from 100% ground state to 100% excited state, in the middle 50-50 here. This is on the lowest qubit here, either 0 or 1. okay? And that is the qubit 0, which is the input for Alice's teleportation. And it's going to end up as Bob's last qubit. But we put different patterns in here. The second qubit has been, in this circuit, it's 100% 0. We're moving it in different superpositions. This should be 85.4% and 14.6. So that we can see the effect of these qubits on the channel. So we can see immediately that the L gate here, the first L gate, changes the probabilities or the magnitudes, and these are reflected in different state probabilities here. And then we have a C0 gate here, and that changes the pattern again. So that's the first half. We can see the second half here. This is a pattern from the last slide, going through another C0 gate here, and then finally through an R gate. This is the output of Alice's circuit, where all of these, in each circuit, each qubit is in a 50-50% superposition, made up of different combinations of these state vectors. So that is the output, and that's output as the QPS state that was previously described. So in Bob's circuit, which is completely separate, we have loaded up similar circuits, and then we've taken the QPS and teleported in that entangled state into these circuits. And we again we've got 10 circuits shown here out of the 41 or so. And here we actually take that entangled state, which is all ambiguated, and we come up with the output of the teleportation, which is Bob's bottom qubit here, qubit 2. And we've given these labels in German. So his qubit has got the German labels coming out here. And we can see 0, 1, 2, 3. So that is basically the overview of how the Bob circuit works. And here it is in action. So this was the QPS state that was teleported in. You can kind of see the same pattern that was from Alice's circuit. And then it travels through this circuit of quantum gates to the output. Now, in this output state, this is qubit 2 is Alice's input. The interesting thing about this is this was dumped for each of these gate-by-gate circuits, and it shows actually that this first C0 is really the critical operation. The rest of these gates are to do with taking these qubit 0 and qubit 1 and putting them into a 50-50 superposition, and the output being on the last one here. So functionally, what have we got out of the circuit? We can describe from the different combinations that Alice's qubit here, qubit 0, gets teleported to Bob's second qubit 2 here via the QPS. But this only happens, is conditioned on Alice's qubit 2 here. So we have a formula where the Alice's qubit 0 and qubit 2 are combined to yield Bob's qubit 2 here. And essentially the takeaway is that qubit 0 is the channel, qubit 1 is actually a don't care, and qubit 2 is a channel sense, such that when the qubit 2 is in 0 state, Alice's qubit is faithfully teleported to Bob, and if Alice's qubit 2 is in a 1 state, the teleported qubit is swapped in 0 and 1 states. And if Alice's qubit 2 is in a 50-50 superposition, then the output is also, the Bob receives is also a mixture of Alice's states, such that no information is actually teleported, and it's a nonsense mixture. So next we've got the web-based quantum teleportation where we're sending the QPS via a JSON web signature and a JSON web token, showing that this can be transported over the conventional internet. Finally, not finally, this is the next to last slide. We've got an application how the QPS can be used in a quantum key distribution, because the QPS naturally has a conjugate where each state vector's complex magnitude, the imaginary component, is negated. So the same probability, but actually the mirror image in the complex space. So we can have a scheme where circuits are processing these pair in parallel, they exchange measurements, and these can be used to confirm that the pair is entangled. Finally, we have, just for context, we're showing how the QPS can actually evolve from a measurement. So it's in a superposition state here of a mixture of 0 and 1. And according to the probabilities, which is defined by the square of those complex magnitudes, we have a PDF, or probability distribution function, that can be sampled to create an observation. When that happens, we combine the non-observed state vector magnitudes with the observed state vector magnitudes according to a root sum of squares addition. And that is the end. I'm open for questions if anybody has them.
All right, thank you. There's applause in the room, which you may or may not be able to hear.
Thank you very much.
Since we're running a little short on time and we've still got 2 more presentations, I'd actually like to go on to the next presentation. So if there's anybody who has questions for Roger, please ask them in the chat. All right. So let's see. Next presenter is Diego about about the ongoing draft multiplane architecture proposal.
Okay, I will try to be as short as possible. Well, I guess I have more than 30 seconds.
Momentarily, you will have more than 13 seconds on the clock, yes.
Okay, so the idea, this is another iteration on this architecture framework draft. This is just a review of why we started this and the reasons why we believe this is important. Because what we were thinking starting working on this was about providing a general framework that could help us in reasoning about the different protocol definitions and the APIs, etc. If you think about it, today, for example, we have been, at least in my impression, that there are a couple of presentations talking about precisely the classical and quantum alignment and how we coordinate this. And we believe that providing a framework that would help us in exploring this coordination, for example, and exploring how we can deal with the propagation of classical information, how it corresponds to the quantum information, how we can relate other aspects, like, for example, the physical connectivity. If we want to build a real network, we will need to have the possibility, for example, of creating physical connectivity on demand as well. Then we have the entanglement, and this doesn't need the physical connectivity, etc., for sure. But we need to start with this, and this is the idea of coordinating all these aspects and making converge the different control, forwarding, and other mechanisms. With the idea that, apart from that, what we are trying to leverage is something that there is already real operational experience in running QKD devices, infrastructures. We and other network service providers worldwide are experimenting with this. We are distributing keys. We are providing service to our customers based on this, and we have this experience that, for sure, QKD has a much narrower scope and is very much focused on a particular goal, but it's important as well to learn about this operational experience if we want in a certain moment to build something that we can consider a quantum network, or even better, a quantum-enabled internet in which we can integrate the current internet and quantum principles. For that, basically, we took some based on the SDN concepts, and again, many of the speakers that were today ahead of me have been talking about applying implicitly or explicitly SDN principles to, we're talking about control planes, about forwarding planes, about control messages, etc., and building the whole thing, and well, based in a particular architecture that is not only multi-plane, but is multi-strata. That is important because we're talking about dealing with the connectivity, dealing with the classical network, and dealing with the pure quantum effects in an integrated view. That's the idea behind this the architectural framework. For this, we have developed in the last 2 or 3 versions the idea of a service unit in general, and a service unit is no more, no less that the way of identifying a shared state between 2 application entities. We are trying to step away from the idea of saying, no, we are talking about a flow, or we are talking about a packet, or things like that. We are trying to use more neutral terminology to allocate precisely for the different options that we have. And when we're talking about a service unit, that means it's a shared state. We are sharing, in the case of QKD, we are sharing a bit strings that can be used as keys. In the case of a general entanglement network, we are talking about one or a number of entangled pairs that can be used for whatever according to the criteria of the application. And that is why we're talking about that. It's something analog, not exactly the same, but it's something analog to the transfer flows. You remember the famous 5-tuple of the source address, source port, destination address, destination port, and protocol. Something like that. When we're talking about this and we're trying to identify how to address these service units, we're talking about identifying it for the moment with URNs, which is something very, very, very neutral and very general, precisely with this idea. And with the idea that these mechanisms would allow us a powerful abstraction to reason about properties at the different 3 strata that I was mentioning, the physical connectivity, the quantum forwarding, the use of for the application, and applying principles for routing, for access control, from accounting, and for whatever other function that are related to how you operate and run an infrastructure in that is intended to provide a network service. These are the foundations, so to say, since last time, and taking into account that in the middle we have the summer break, that doesn't help very much in being very productive. We have worked in 2 aspects. One is there is a section in the draft about identifying protocols and interfaces. We have started to identify which are the different proposals that could be applied and how. When talking about the connectivity and physical connectivity, optical connectivity, basically, we're not considering yet anything that has to do with satellites. This is something that could be an interesting issue. There are solid references, and we have taken the work that has been done by the ACTN group in the routing area, if I remember well, or it's internet area. And specifically, something that would be highly desirable, I believe, is that, given my experience, is about a path computation element. And I'm talking about a physical path computation element that you decide you want to establish entanglement between 2 points, and then you find a physical path that would help on that. When talking about quantum forwarding, and well, we have started analyzing proposals that now we have seen, like the one Marcello was mentioning on the quantum native addressing and routing, etc., and how this could fit within the framework, and some consideration on quantum repeaters. That, again, there are not that many physical quantum repeaters available yet, but still the theory and how this could be used we are starting to analyze it. And when we're talking about the service and this concept of the service units, is precisely how we can provide a map that reflects physical connectivity and the entanglement overlays on top of those of the physical connectivity topology, how they can be related to the service units, and how we can deal with one of the characteristics of the service units as well. We were talking about how they are parameterized, and the idea how this parameterization happens. The other part that we have been starting to work is the idea of synthetic environments. If we want to make and analyze the properties of what is being proposed, etc., for analyzing these proposals is, that using current testbeds is something quite interesting. But if you look at the testbed, the testbeds are quite limited in scale. We're talking about a few nodes maximum, few links, because it's complicated, it's expensive, and it's difficult to keep and make a detailed experiment. So our proposal is to go a step further from the current simulation mechanisms and start focusing on emulation. And the idea is that we can emulate a distributed quantum system and the interaction with physical classical mechanisms. So we can explore this idea of the service units. We can explore how a particular quantum routing mechanism can live together with the physical virtual machines that are implementing the different features, etc. And to do this at a certain scale that goes beyond what we can do right now experimentally. And going up on scale that, well, that depends on, yesterday we were talking with Rod and Bob about this, about the idea that how would be the real scale that can be achievable. We have started with well, a couple of tens of nodes, but probably, if we can move, and we have a discussion with some of my authors, because I was very seriously saying that we have to commit to get to thousands of nodes. I'm not totally sure, but well, let's see. And the idea is that with this, we can play with these proposals, and we can play with going a little bit beyond what you can be verified by simulation. And try, even one of the things that we have in mind, if you look at the diagram is not very clear, but the idea is that you have, it's not very clear because it's too small to fit it there. But the idea is that every single quantum node has a different quantum emulation engine that is basically a simulator, because we're not talking. And the idea is that to make them independent, use different models, validate the different models, see whether those different models make sense depending on the underlying technology that is on the hardware, or even something that we have already achieved, because we have this element right now running for QKD, and what we have already achieved is mixing real nodes, physical boxes that are implementing QKD with emulated nodes to make some experiment. The idea is to report this and to make some experiment on that. Just a quick note: we are seriously working on the parts of the quantum emulation engine and problems that are related to how you synchronize time in the simulation, in the simulated environment, and you take into account for the effects of time as well when you go out from the simulation environment into an emulated node in which things happen without a total control on the experiment. Just to finish, our idea is to, well, we are willing to progress with the draft. We believe it's mature for adoption. That means, just as a reminder, it means that there is interest in the group that thinks that this work is worth continuing. And what we intend, let me say, is not that we are not trying to propose the set of protocols for the quantum internet or whatever. It's the same way that probably, and allow me the analogy that probably is a little bit too ambitious or too pretentious. That the same way that the layering, the original layering of networks, whether it was it was internet or it was the OSI or it was whatever else, the idea that you have to separate the problem into layers and solve the layers issue is something that is useful. What we believe is that this idea that you have to consider several different dimensions in parallel and coordinate them is something that is worth to be considered here, and that what we provide, or we're trying to provide, is a reference framework that can be used for defining a methodology, for evaluating protocols, and think that there will be very likely the same way that there is no one single protocol in the internet, with the exception of this idea of the hourglass, that we have a IP and it's IP over everything. Probably there will be a single protocol that will deal with the network itself, but the rest of things are going to be wide. And the idea is to have something that helps us in reasoning about this wider world, and trying to identify research issues. When talking about research issues, have a common reference, and we say, no, I'm trying to do this for this part, or I'm trying to do that for this other part. So providing a common framework for that. In my view, this is an essential role for a research group document. It's not a standard. It's a framework, or it's a common ground to which discuss and to have the base for that discussion. And that's all. It's just, I have turned the clock red, but well, I hope it's time for some comments.
All right, we are running still a little behind schedule, but I think we can take about one question here if anybody's got a question. If not, I actually have a comment, sort of semi as chair. The content of the current draft contains a lot about the current state of the art and sort of a lot of thinking out loud. And as we try to finish the draft and turn it into something that's long-term useful, we need to look at whether or not that's the right level of content we want to have in it or not.
Okay, so well,
let's talk about that this week.
Yeah, definitely.
Anybody else real quick? If not, we can move on to the last presentation, which will be about the new internet draft that just appeared like magic out of nowhere on October 1st. Let's see. Oh, Alan, I think he's actually, yeah, Alan's doing the presentation remotely, right?
Yes.
All right. Also, we're same as with the last remote speaker, we're a little loud here in the room, so if you can either speak softly or shift your mic away just a little, that'll make it a little more comfortable here in the room.
Okay, is this good?
That's perfect.
Okay, perfect. Good morning, everyone. My name is Alan Zhu from the University of Pennsylvania. And today, so over this past couple of months, we were recently working on a new quantum datagram control protocol for IP optical environments following some successful experiments that have been published in Science on doing a classical plus quantum hybrid internet style distribution. So first, what the reason why we chose this sort of datagram procedure is particularly because of the no cloning theorem. So right now, we kind of have the classical information in our QDCP protocol, which is basically just a lightweight control metadata for the quantum packet itself, and then the quantum packet following that. And currently with our work, these two aren't really separated. So because of that, because the quantum information can't be cloned, we just have that as a single datagram. And already we've, as I've mentioned, done experiments to demonstrate this hybrid quantum classical packet routing on commercial fiber. And we're able to successfully go through a commercial network using the classical packet as routing and metadata information, followed by a quantum packet that is generated on chip using integrated photonics. So for our actual packet design, so as I mentioned, this is built on top of UDP as a datagram. So we'll have the initial UDP header, and then will be followed by the QDCP header, which will include version, flags, the length of the entire packet, and some reserved bits, followed by the bulk of this packet, which is the type length value payloads, or TLV payloads. And there can be a multitude of different TLV payloads depending on the use case that you want. Currently in the draft, we've defined, I think, about 9 of them, specifically for things that we were considering in our experiments. But this list can definitely grow, and we can have many different TLVs that we can define. And these TLVs can also be strung together sequentially. So we can have a single QDCP packet that contains 4, 5, 6, however many TLVs, as long as those fit within the length of the entire UDP packet. And we'll see an example of that in a little bit. So for our current TLV type assignments, like I mentioned, we have a couple. Here's just a list of them, and I wanted to point out a couple that really kind of we needed in our experiments. So the first thing is if you look at 04, we have the reconfigurable optical add-drop multiplexer output port ID. So this is something that we use in order to configure the switches, so that way the quantum packet would be able to go in the right direction based off of the destination IP. We also have 05, which is quantum packet delay. So this is delay between the actual classical packet and the quantum packet when you're sending both of those. And then, of course, we also have duration of the quantum information itself. So this is just to make sure that you are reading the quantum information when you should be and not when you're not, just to maximize any signal to noise ratio that you have. And also for 09, we have the polarization correction. So experimentally, the polarization of your quantum information and your classical information, but that doesn't really matter as much as it's traveling through the fiber is going to change. And I'll get into this a little bit more right now. So especially as we're doing kilometer scale distance fibers, such long fibers will ultimately have some polarization shift on the light, and you can model this typically as just some arbitrary SU2 rotation on the Bloch sphere. And so the way that you can address this is you can actually use classical light to identify for this change and correct for it for the quantum information. So here we're just making the key assumption that whether it's quantum or classical light, the polarization itself will undergo the same rotation through the fiber, which is a valid assumption, at least that we demonstrated experimentally. And so for actually correcting the polarization, so essentially we can define a TLV, which we define as type 09. And then for the reserved bits, we actually can just define a bit mask for the types of polarizations that are known and that are being sent from the sending chip. And so, for example, if I wanted to send right circular polarization and horizontal polarization in order to do this calibration, then in the reserved bits, I would just bit mask bit 4 and bit 0. So that's telling the receiver that these are the types of polarizations that it's going to receive. For the length of the polarization correction, we fix this to exactly 32 bits. This is because mathematically, only 2 polarizations are actually required to recover the full SU2 transformation that the fiber applies onto the light. And so just for simplicity and to make it so this packet doesn't extend very long, because it should be something that's done quickly and then followed by the quantum packet, we just limit this to 32 bits. And then for any polarizations that aren't actually used, you can just grease them according to RFC 8701 and just ignore those bits. And so here, this is the full example of what that TLV would look like if we're doing a right circular and horizontal polarization correction. And if we string all of these together, what that might look like is we have a chain of TLVs. So we'll have the standard UDP header followed by the QDCP header. And then for the actual TLVs, what something might look like is if we're trying to send a quantum packet from our transmitter to a node specified by its IP, we can first send a TLV 04, which will configure the ROADM. So that tells you, for example, if I want to go to node 192.1.2.2, the ROADM will configure correctly, so that way the correct switching path is pointing to that node. And then we can send the duration of the quantum information in the next TLV, so the node knows how long to read the quantum information for. For step 3, we can send TLV 05, which is the quantum packet delay. And that'll actually tell you how much time, once again, is between the classical and the quantum information. Then for step 4, we can send the polarization correction. So using the example from before, we can send the right circular polarization and the horizontal polarization, and the node can receive that, and it'll know based off of reading from those polarizations what adjustments it needs to make on its end, so that way the quantum information arrives correctly at the node. And then you can actually send the quantum information. And an important thing to point out here is in this application, although the classical QDCP header itself is limited by whatever protocol you're using, say UDP, the quantum information itself doesn't actually have that limitation, because the classical header is just configuring the switch and it tells you how long that's going to be. I guess technically there's a length that that number of bits that the quantum packet delay can be specified to, but it's very long. The quantum packet information will never be that long. So the quantum information itself can be as long as you want. It can be seconds, hundreds of seconds. You can just continue to send quantum information through that route. And one more thing is in the bottom in this graphic here, if you take a look, we have Lambda 1 and Lambda 2 listed. And this is just really to show that the reconfigurable optical add-drop multiplexer can actually support different wavelengths simultaneously. So Lambda 1 can go to one direction, Lambda 2, different wavelength can go to a different direction, and those can exist in the fiber at the same time. Of course, with these kinds of things, there are security concerns. So QDCP is just running on top of UDP, so it inherits all the risks of UDP, such as spoofing, injection, and replay. Obviously, these things don't exist for the actual quantum information, but for the classical information, you still inherit these risks. So we say that in this draft that it must be run in trusted environments or protected by DTLS or IPsec. And also, these TLVs can reveal network state information and must be protected if confidentiality is required. We are in discussions of some future work with compatibility with TCP or QUIC for the classical header before sending your quantum information, but we can talk about that later on if anyone is interested in that. We'd also like to thank Steve Schwab and Wes Hardiker for their constructive feedbacks in getting this draft kind of online over this past month. It's been kind of a rush to do that. And thank you for listening. If you have any questions, comments, concerns, I can take them now, or you can send them to me, Yichi, or Robert at our emails below.
All right, thanks, Alan. Applause here in the room. I would like to have a long discussion about this, but since we've had a full agenda today, we're actually right at the end of our time here. My jet lag and I did send a long email message on the mailing list early this morning, and I gather you guys are renaming the protocol, and you have what should be a -01 version of the draft ready to submit. But if you rename it, that will go into the system as a new -00, and then the chairs, we can associate those two together and say that the new one replaces the old one.
Okay, perfect. Yeah, I actually submitted it earlier today when you told me it was going to open today. So should be there.
Okay, I haven't seen it in the data come through in the data tracker yet.
Okay.
We'll talk to Robert here in the room after this ends. Let's see. So it is already, well, according to my clock, 1:31 a.m. But let's see. Any final comments or questions from anybody here in the room? So David Rowan says good meeting. We had a lot of ground to cover, so thanks everybody for being cooperative on the schedule. Personally, I plan to be in Shenzhen for IETF 125 and to hold a QIRG meeting there. So we'll see you all on the mailing list. And since it is Monday, you can still find many of us here in the hallways throughout the week. And otherwise, we'll see you on the mailing list. Thanks for everybody for attending. And thank you for your help.
Yeah, you're welcome.
Particularly the first 15 minutes or so for every time I'm doing this is always a little on the chaotic side.
Yeah.
So
Yeah, I've done the. So it was funny. I was telling people, it's like, oh no, I'm doing, this morning. I'm gonna go over and help Rob. I'm gonna fly right seat, and I was very happy that you gave me the actual right seat.
In a helicopter, it's the other way around, right?
Yeah. I don't believe in helicopters though.
Have you been in one?
I've never been in. I try not to get into any device that has a part that's called the Jesus bolt. That just seems. I'm an SRE. I like N+1 redundancy on.
Do you remember? Are you old enough to remember the VMS TCP/IP stack?
My first access to the internet was via a VMS machine, and I probably used it because I mainly used it to just run SLIP.
There was before DEC had their own TCP/IP. There was a small company called TGV that provided TCP.